Okay, I wanted to quickly mention the video I have on the screen here. I call it Category Theory and Card Magic, that looks at what are called quasi-Bessey sequences of order 4 and a wonderful application of that structure. So if you get a chance, it might be worthwhile watching that first and then coming to this video, okay? It's not absolutely essential, but it could prove helpful. Or at the very least, watch that video after this one because they're reinforcing videos. So to begin, we're going to compare and contrast two different abstract algebra teachers here. Okay, so the topic for today is the dihedral group of order 8. And so teacher 1, the beginning of class, he holds up a square similar to this one here as a motivating example for the dihedral group of order 8. And so what he explains is there are 8 different ways that you can rigidly move this square and essentially have its footprint the same. So for example, right now, if we were to rotate the square 90 degrees, it will be indistinguishable from what it was before. Another 90, same thing. Another 90, same thing. And then technically, if we do 90 again, we've rotated it 360 degrees. So we're truly back to where we started. What are some other ways that this square can be moved in space and stay the same? Well, you can do a horizontal flip like that. You can do a vertical flip like this. Or you can do 2 diagonal flips like this one right here. Or you can come over here and hold it with the other hand and go like that. And then, of course, as we know in group theory, there's always the do nothing element, the identity. So all of those added together add up to 8. So there are 8 rigid motions of the square that will leave it the same. Okay, so that is our motivating example for the dihedral group of order 8. Okay, I want you to compare that introduction with doing that, but following it up with a second motivating example. Okay, so as you can see here, so this is like teacher number 2 has just done what teacher 1 did, but now is going on to try to give a motivating example that may serve as more motivating than just moving a square around in space. Okay, so he shows 4 cards with jokers on the ends here, and some cards in the middle, a king and a queen. And then he asks the class, are there any jokers out there? And of course, some hands will probably go up. And then he says, well, what I have observed regarding jokers is that they always seem to gravitate toward one another. They will always find each other in the end somehow. Okay, so let's just kind of demonstrate this here. So everything that we'll do will be with the cards face down. None of us will see the faces of the cards, okay? So I'm going to give you a whole series of choices. These are free choices. And I'll do whatever you've asked me to do, okay? So I'm going to deal out into 2 piles, like this here. Would you like me to stack left on right or right on left? Your choice. You want right on left? Okay, very good. Why don't we do something called a Australian down under? That's a famous shuffle, actually. This is where you go down, under, down, under, down. Last one goes on top. Another great shuffle is an up jog. Some people call it an out jog. So this is where you jog forward. Let's say the even position cards, strip those out. How would you like these stacked? Left on right? Okay, that's just fine. Have you heard of the Pharaoh shuffle? It's perhaps the most famous shuffle out there, the Pharaoh shuffle. Would you like an in or an out? You want a Pharaoh in. Okay, so this is where I divide it in half, and then the top card over here goes inside the other, underneath the top card on the left. Okay, so that is a Pharaoh in shuffle. There's also something as simple as a reversal. Okay, so very simple, but kind of an important way to mix cards along with others. We can do a Charlier 1. Okay, And that's something I can show you how to do if you would like, but that's called a Charlier once, top to bottom, bottom to top, top to bottom. Here's something called a pairwise transpose. And then we can stack from left to right or right to left to right. Okay, very good. Okay. Would you like me to do any more of those? Which one? The Australian down under. Okay, most people like that one. Down, under, down, under, down. Last one goes on top. Okay, so I think you would have to agree that no one could have followed where those cards are very easily, if at all, actually. Okay, but I'm going to separate them into pairs, and I have never missed this. I've always been able to put the jokers together for the simple reason they want to go together. Okay, so it's actually easy for me to do. So what I'm going to do is I'm going to hold the cards just like this, and I'm going to take the top and bottom off as one and set the other two cards down as a second pair. So let's check. Oh, there they are, upside down. Of course, they're messing around. Indeed, those silly little jokers found each other. Well, believe it or not, the very actions that we talked about here constituting the dihedral group of order 8 are also analogously the very actions that we performed just now on this packet of 4 cards that enabled me to separate with 100% confidence the jokers from the face cards. Okay. In fact, let me just show you a comparison of the group elements in these two expressions of the dihedral group of order 8. So I'll bring that up. Okay, on the left-hand side of the screen, you'll see a listing of the group elements for the symmetry group of a square and the symmetry group of a quasi-Bessey sequence of order 4. So let's go ahead and just kind of review what that is, actually. So what is a quasi-Bessey sequence of order 4? Well, it's one of these two sequences, 1, 0, 0, 1, or 0, 1, 1, 0, where the zeros are equivalent to one another but distinguishable, and the ones are equivalent to one another but distinguishable. So like in the sense here, the jokers, we would consider them equivalent, but they are distinguishable. This one's black for one thing, this one's red, okay? And then we might associate the face cards as zeros. Well, as face cards, they're equivalent. They're both face cards, but they are distinguishable. One's a king and one's a queen, right? So on the left-hand side of the screen, what I've done is I've listed the different shuffles that we use. Well, we didn't use all of them, but the different shuffles we could use that correspond to the rigid motions of a square that would leave it fixed. So for instance, the diagonal flips, there's 2 of them. One of them corresponds to a left-right dealing in which the right pile is stacked on top of the left, or the down-under, Australian down-under shuffle, or even dealing out into 4 piles, which is not what we did, but we could. The other diagonal flip corresponds to an up jog in which the odd position cards are stacked on top of the evens, or equivalently, the pharaoh out gives you the same rearrangement of the cards. A 90-degree rotation corresponds to an LR shuffle in which the left pile is stacked on top of the right, or a pharaoh in, or another dealing out into 4 piles with a particular stacking of those. The 180-degree rotation corresponds to a packet reversal, which in some ways is not surprising, or another dealing out into 4 piles with a certain stacking of those piles. A 270-degree rotation corresponds to an up jog in which the even position cards are stacked on top of the odds, together with a dealing out into 4 piles. The vertical flip is a 50% cutting of the cards, or a Charlier 1, which is equivalent. The horizontal flip corresponds to a pairwise transpose, or a dealing out into 4 piles with a certain stacking order. And then the identity transformation for the square, of course, corresponds to the identity shuffle. So in the case of the square, we know that its, quote, footprint is being preserved, right? We're looking at rigid motions where it brings it back to the same configuration of the square, right? Maybe a diagonal flip like this, vertical flip like that, and so forth. Well, in the case of the 4 cards, what's being preserved? Well, supposedly this structure right here. So let's quickly look at that. So if you associate the red card as a 1 and the blue or black cards as zeros, this is like having a 1, 0, 0, 1. Okay? So if we go through and check any of these shuffles, we'll see that we'll either get this packet back or its inversion, where the red and blue cards switch places. So for example, the very first one, number 1, left-right shuffle, in which we stack the right on top of the left, it preserves that structure. We still have a red on top, and then the 2 blue in the middle, and then a red at the bottom. So all of the ones marked in red preserve the structure as is. The ones in blue invert it. So for example, if we do a 50% cut, so if I go like this and then cut those to the bottom, of course we have switched the colors, right? So now it's going to be blue, red, red, blue. But with those shuffles here, it will always be the case that either it preserves this configuration here or it inverts it. So the colored cards switch places. That's all that means, okay? And then to study it further, what we can do is we can go ahead and give subscripts to these particular values. Okay, so if you think of this as 1, 0, 0, 1, this is like the first 1, this is the first 0, the second 0, and then the second 1. Okay, so as we go through and mix this, maybe we can do a pairwise transpose like this, stack left on right. We can see that not only have the zeros and ones moved around, okay, so we now have zeros on the outside, ones in the middle, but we can see what has happened to the particular zeros and the particular ones. Have they preserved their relative ordering, or have they been switched in some way? So I wanted to put this chart out into the educational world here as a motivating example for not only groups that students can relate to, namely packets of cards here in which you pull off something very surprising. This also shows that group theory applies in situations where it's not immediately clear what structure is being preserved. So the preservation of structure here for these quasi-Bessey sequences of order 4 is that the sequence structure is exactly preserved or it's inverted. One of those two things will have to happen if you apply an element from the dihedral group of order 8. And to my knowledge, I have not seen anywhere where the dihedral group of order 8 has been applied to a packet of cards that leads to a very surprising result. And to finish, what I thought I would do is just quickly show you the background information for what you're seeing here. And so what I'll do is I'll just quickly show each page for just a few seconds. Anyone interested could pause and then read it and then go on, okay? So I'll just quickly step through the pages of the analysis that led to what you see on the left. Okay, so here I have the symmetry group of Bessey sequences of order 4. I give a list of preliminaries to set the context. I give the analyses as to, okay, how did I come up with the dihedral group of order 8 as being the symmetry group for quasi-Bessey sequences of order 4. Okay, and then I list generating sets for this group in terms of the very shuffles that we've been looking at here. And I give you several minimal generating sets that you can use. I've also listed what each of the shuffles corresponds to in terms of a rigid motion of the square, okay? And then I point out that since it's a quasi-Bessey sequence instead of a full-fledged Bessey sequence, it doesn't have the same degree of symmetry that a Bessey sequence has, but there are judicious pairings of shuffles that can be applied to enlarge the repertoire of shuffles that will either preserve or invert quasi-Bessey sequences of order 4. Okay, so here's some right here. And then I even talk about surprisal So in the description below, I will also add a link to my playlist on Bessey sequences and quasi-Bessey sequences if you want to look into those further, because a tremendous body of card magic has been created using Bessey sequences and quasi-Bessey sequences of various orders. So you can take a look at that. I'll put that in the description below. Okay, so that is what I wanted to share with those interested in abstract algebra and in particular group theory, and maybe even as an encouragement to teachers who are teaching the subject to students for the first time. Consider including an example, such as the one I've shown here, where the invariant structure is not one of the common ones. And so this is an original result here, so you're not going to find this in a textbook. You might in 20 years or something, but it's not there now. So anyway, this is something fun that many of the students will relate to and find to be a bit more engaging and motivating than stopping the discussion with just the standard examples given in the textbooks. Okay, so thank you for watching, and take a look at other videos on the Absolute Math Magic channel. I have quite a few on group theory, actually, the Klein group and so forth. So take a look at those, and I think there'll be things there for any of the math teachers out there, actually, and students as well. So if you want something cool, most people don't think of group theory as cool, but in the case of card magic, I think it is. So thank you again.